Hello, everyone. I will be discussing optimum value selection of Q-learning parameters in stochastic mazes in the following aspects. Well, first of all, let me give a brief introduction about Q-learning. The theoretical foundation of Q-learning algorithm includes MDP and Bellman equation. MDP, Markov decision process, which means the next state is only relevant to the current state. And the Bellman equation, which is used to update the state action value function in Q-learning. Besides, DEP, which means the dynamic programming, MC, which means the Monte Carlo, DT, which means the temporal difference. These three approaches are able to help us dive deeper in understanding Q-learning. And also Q-learning is actually given birth by these algorithms. Well, furthermore, the idea of policy improvement is also used in Q-learning, and the trade-off between exploration and exploitation should be found in Q-learning. Therefore, the goal is to implement fine-tuning Q-learning algorithm in several randomly generated mazes until the agent finds the shortest path and remember the path. The criterion is that the agent reaches the endpoint and the path length eventually be convergent. Also, the visualization result of the searching path progress will be presented. Okay, there are three main keys during the experiment. First and foremost, the algorithm should be tested under a large number of mazes with different layouts of the obstacles. In this way, the result will not diverge too far with individual differences. Second, in order to make the whole circumstances closer to our real life, the oblique motion is introduced. The detail of oblique motion will be shown in the following section. Third, the appropriate learning rates will and the discount factor should be found, since an optimum values can result eventually in great outcome. With the following analysis and comparison with when the learning rates and discount factor are both set to 0.9 can lead to a better outcome. Okay, from this slide, the pseudocode of Q-learning is shown in two forms. The table on the left side is more precise, explaining every detail of the requirements and the algorithm. Besides, the flowchart on the right side is more succinct, demonstrating how an initialized Q table becomes a good table at the end. Okay, let's move on to the part of setting. On the left side, the figure 1 shows 5 stochastic mazes generated by the algorithm. The size of each maze is 20 by 20, and the agent will search the path from the point of SP, which means the start point in the upper left of the maze, all the way to the point of EP, which means the endpoint in the lower right of the maze. On the right side, there are some given rewards of movement and are the given values of parameters. For example, the value of I minus n can represent the movement of turning movement of going up, or the value of I minus 1 can represent the movement of turning left. The word percentage means the blocks number of the obstacles occupies 30% of the overall maze size. About the learning rates and the discount factor, I will do further discussion to everyone. Okay, from this slide, the figure 2 shows the visualization result of the shortest path that the agent found under the certain values of the learning rates and the discount factor. The figure 3 shows the progress for every 8 iteration of searching the path. The total number of iteration is set as 80. Since the map is an epitome of the real-life transportation mazes, therefore, there is no need for us to get a better result at the expense of computational consumption. Nevertheless, when it applies to real-life issues, the iteration should be adjusted simultaneously. Okay, so from this slide, I'm going to show everyone why I use 0.9 to set the DF. First thing first, DF represents discount factor ranging from 0 to 1. The closer the discount factor towards 0, the more agents tend to consider the short-term benefits. The higher the discount factor, the more agents are concerned about the future, which is long-term reward. In the figure 4, we set learning rates equals to 0.9 as invariance, and the independent variable is discount factor. We compare the data when the discount factor equals 0.1, 0.3, 0.6, and 0.9. The result of which shows that with the discount factor increase, not only the earlier time of finding the shortest path it can arrive, but also the shorter length of the final path it can reach. As a result, when discount factor equals 0.9, it can find the shortest path in a relative short times of iteration, about 14, and the final path length is about 26.7. Therefore, we tend to choose 0.9 as the value of discount factor. Okay, from this slide, it's another comparison between different values of learning rate. First of all, when updating the strategy, there will be a difference between fast speed and slow speed, the term of which we call the learning rate, ranging from 0 to 1. In the figure 5, we set the discount factor equals to 0.9 as invariant, and the independent variable is learning rate. The figure 5 shows that with the learning rate increasing, the iteration times of finding the shortest path can be reduced, which can conduct a better result if we introduce these values, that alpha equals to 0.9 to our algorithm, to some extent saving the computational consumption. Okay, based on the previous 2 analysis slides, the conclusion can be drawn that when the discount factor and the learning rates are both set as 0.9, the respective result is great, which means these 2 values are pretty close to 1. But a confusing point comes to my mind that why shouldn't I just set both the discount factor and the learning rates to 1? And this slide might help us figure out the issues. From this slide, I compare our 4 groups of data when the discount factor and the learning rates are both set as 0, 0.1, 0.9, and 1. So we can infer the reason why 0.9 is better. From the formula showing in the top of the slide, when the learning rate equals 0, the O value that QST80 will be counteracted, which means the agent will take actions based on its speculation without any experience from previous iteration. If the discount factor equals 1, the future rewards are as important as the current one, which means that the agent is far-sighted. It can see from a big picture, but it also means that the agent will be ambitious to try every possible path, and this requires more resources and time. And also, if the discount factor equals 0, there will be no consideration of future. Therefore, in this way, local optimum might occur. Okay, at the end of the experiment, the conclusion can be drawn that when the learning rates and the discount factor are set as 0.9 can conduct a better result. That's all. Thank you.